So we are going to continue along our journey of taking what we know about derivatives and reimagining those things in the context of functions of several variables. And I think so far we're making good progress. Well, there's an important concept from single variable calculus where if your function is sufficiently nice, right, you can repeat the process of differentiation. Well, it turns out that's also true for functions of several variables. In other words, what we're going to look at in this video is look at the concept of, what do we mean by a second partial derivative, or a third, or a fourth, if they exist, right? So before we get, again, too far down into examples, let's talk about some notation, right? And the thing with the notation is, because we now have several variables that we can be differentiating with respect to, right? Could be two or more. Then there are more possibilities for higher order derivatives, right? It's not like you just have an f of x and then an f prime and then an f double prime. That's because we only have one independent variable. But if we have several, right, we have to be clear on how do we denote these higher order derivatives. And again, just for simplicity, let's start with the case where our function is a function of two independent variables, right? So again, just as a reminder, remember, so these are functions where now you'll take ordered pairs with the hopes of producing a real number, right? Well, so let's see what we know about this. And we know, as far as first partial derivatives of a function like this, there are two possibilities. It could be either a first partial with respect to x, and I will denote it the two possible ways like that, or a first partial with respect to y, and again, these are the two standard notations for that. But the thing is, both of these now are themselves functions, so we could technically differentiate this one with respect to x again, or we could switch it up and we could differentiate this one with respect to y, right? So similarly here, we could have our first partial with respect to y, and then for possible second partials, we could continue differentiating with respect to y, or we could take this function and then differentiate it with respect to x. And that's the variability, or not really variability, but that's the possibility now that we have, because we have these several variables. So let's say we wanted to indicate what taking this function, which is our first partial with respect to x, and then differentiating a second time with respect to x. So here, so it's like I would take this function and I would differentiate it again with respect to x. So really, with the parentheses and trying to write this even as a lower subscript than the first one, that doesn't really, we don't gain anything by doing that. So we condense this notation and just say f sub x, right? So, if you differentiate twice with respect to x, this is what it looks like. Now, with this one, this is where you would be differentiating this with respect to x. Now, with the d notation, it looks like this. Right? So it looks like that. Right? And again, we've used this notation previously, but that's when we were going through specific examples. But now this is a general notation, and it still applies. And what we can do, instead of writing this, we could say, okay, we have like these two d's in the numerator, and then we have these two dx's in the denominator. So I can condense this and write it as d2f dx squared, right? So these are the two notations that we typically use to indicate when we have a second partial derivative with respect to x, all right? Actually, now that I look at this, if I'm going to do this, I'm going to need some more room. So I'm going to remove this one here, and we might end up going way further to the, or actually, do I? Yeah, let's do this. Right, so this is what it would look like if we differentiate twice with respect to x using either notation. If we took this one and now differentiate with respect to y, so let me, and I think it would be helpful to have these little branches or these lines labeled. So this one is with respect to x, that produces the first one, and this is another one with respect to x. So now what if I took this and differentiated it with respect to y? What would that look like? So let's say this is with respect to y. So I would take this function and then I would differentiate it with respect to y. Using the subscript notation, that's what it would look like. But again, we can drop the parentheses and just say this is fxy. So in this notation, we read it from left to right. So this would be the first variable of differentiation, and then this would be the second variable of differentiation, right? Now, what does this look like with the Leibniz notation? So this is where I would take the partial now with respect to y of the first partial derivative with respect to x. So then I would still have these two d's in the numerator, if you will, even though these are not technically fractions. But then in the denominator, I can't really combine these two. So I just write it as dy dx. So here, if you notice, the order is kind of reversed because this one is saying, again, the process that we're doing is we're differentiating with respect to x and then with respect to y, and that order is going from left to right in this notation. But then look at this, it's in the opposite direction now, x and then y, right? So with the Leibniz notation, the order tends to be reversed, right? So what's the way you read it this way? Let me say it this way. The way you read this so that you have the correct order of differentiation is from right to left, right? And there you go. So we now have two possible second derivatives, right? In a second, I'll say some more about the terminology. But now I can redo this whole process by first doing a partial derivative with respect to y, and then choosing, do I do y again or do I switch it and get x? So I'm going to go a little further out here just so that we have the room. So here's my first partial derivative. This is with respect to y now. And again, we know how that's denoted, either like that or like that, right? And then from this, I can choose to differentiate. Let's say I choose to differentiate this with respect to x. So along these lines, I would end up, so I'll do my with respect to x here. So with respect to x. So this would just end up being f sub y x, right? First y and then x. But with the Leibniz, it would be switched. I would have the 2 here that tells me that it's a second derivative, but then the first is with respect to y, and then the second is with respect to x. Notice how I wrote it backwards there, right? And then the last possible second partial that we can come up with, right? So y essentially. So if I take this And here's our fourth one. So with respect to y, right? These are a little, when you don't change the variable of differentiation, so you have f, y, that's pretty straightforward. And then for the second, it's d2f and then dy squared, right? So this is kind of what it looks like. This is my little tree diagram that shows all these, so these on the first level right here, these are our increasingly more familiar first partials, right? And again, I'm just saying partials as an abbreviation for partial derivatives. And then these now are our second partials. So we got 4 of them, right? The ones in the middle, like these, and these, where it's first with respect to one variable and then with respect to the other, these are called mixed partial derivatives. So these are mixed partials. All right. Now, again, I'm simply illustrating this, getting you with using a function of 2 variables to get you comfortable with the notation. But with examples, which we're going to work through some right now, we will see what it looks like for where we have either more independent variables, let's say 3 or 4, because you can never have too many independent variables, or the going beyond the second derivatives, right? But it's cumbersome, and it's really okay. When do you stop writing it down generally, and when do you get to examples? Well, for us, the time is now. So let's take a look at an example. Let me scroll down here, and so here is our first example, and we are going to find all the second order partial derivatives of this function. So I'll just write down. So it is the cosine of 2x and then minus x squared e to the 5y and then plus 3y squared. So there we go, right? Not terribly complicated, but now what we want to do is to find all the second partial derivatives, which means we have to start with all first partial derivatives. So I'm going to use the subscript notation a little bit more. It's a little bit more efficient. You can write it more quickly, right? But practice writing those partial d's. They're fun to write. So f sub x. So we treat y as a constant, differentiate with respect to x. So this derivative is negative 2 sine of 2x, thanks to our chain rule. Here, the e to the 5y is a constant multiple, so that constant multiple will be brought down. And then I differentiate the x squared with respect to x, so I have minus 2x, and then bring down the e to the 5y. And then finally, this term has no x's at all, so this entire term is treated as a constant when we differentiate with respect to x. So this is our first partial with respect to x. Let me write the f sub y right next to it. The first term here has no y, so its derivative with respect to y is 0, right? This whole thing is treated as a constant. For the middle term, the negative x squared is treated as a constant, and again, it's a multiple, so it comes down, right? And let me just kind of pause here. Notice the difference between when you just have a constant by itself versus a constant multiplying, in this case, a function of y, right? So it's the difference. Is my constant multiplying something else? That's when I bring it down. If it's just by itself, then its derivative is 0, right? So just be clear on when, certain functions will completely go away versus some functions are brought down. Now we have to multiply by the derivative of e to the 5y. So using our chain rule, that's 5e to the 5y. And then our last term, differentiating 3y squared with respect to y, that's 6y. So I'll just go ahead and write this as, again, I like to put my constants and stuff first. So minus 5x squared e to the 5y plus 6y. All right. So those are all the possible first partial derivatives. Now let's find all the possible second partial derivatives. So I'm going to start with the f sub x, and I am going to do it twice with respect to x. So we're going to differentiate this again, right? We treat this now as our new function, and now we're going to differentiate it again with respect to x. So this one, again, due to the chain rule, is going to be negative 4 cosine of 2x. And again, the e to the 5y, because it's a constant multiple, that will be brought down. And when I differentiate the negative 2x with respect to x, I'll get negative 2, and then it's times e to the 5y. Now, if we do the mixed partial, so f x y, so if I look at this and now differentiate it with respect to y, then I get to treat this term as a constant, so that goes away. The negative 2x is brought down because that's a constant multiple, so negative 2x. And then I use my chain rule here, so then I'll get times 5e to the 5y, which I can simplify as negative 10x e to the 5y, right? So this is our first mixed partial, where we first differentiated with respect to x and then with respect to y. And now we get to switch that around. Take your f sub y, and here is our third second partial derivative. We're going to do y, or take our partial with respect to y, and then differentiate it with respect to x. So now that I'm switching, I get to treat the y's as constant, right? So I differentiate this term, and I'll get negative 10. Well, yeah, it is. That was kind of simplified, but let me write down the steps. So differentiating this term is negative 2x, and then bring down the constant multiple, right? And then this is just a constant. It's not a multiple. So then when we differentiate our 6y with respect to x, we'll get 0. And then we end up with negative 10x e to the 5y. And something should pop out right away. Notice that these are equal, right? And there's not a coincidence. There's an important result, and we'll state it after this example that gives us a general explanation as to why these mixed partials are equal, right? Really important theorem, and we'll actually make use of it later on. But now let's finish up, and our last second partial is the f sub y. So take this function and differentiate it with respect to y a second time. So we'll bring down our 5 or negative 5x squared, since that's a constant multiple, and then differentiate with respect to y. When I differentiate the e, I'll get another 5e to the 5y. And then when I differentiate this 6y with respect to y, I will get 6. So here we go. We have our 4 second partial derivatives, 2 of which are mixed and are actually equal. And then we have the second partial with respect to x, second partial with respect to y, right? So there we go. Again, so the process of repeated differentiation, my mantra is, if you can differentiate once, you can differentiate as many times as you'd like. Again, provided the function is differentiable, or differentiable multiple times, right? So let's address this issue here. Now, the theorem that guarantees this is by a French mathematician, Clairaut, and it's not something that we can prove in this particular course. The proof is beyond the course, what this course entails. So I'll just state the theorem. And now I'll state the theorem the way it typically is stated for functions of two variables, but I'll illustrate how it actually applies to functions of more variables and not just second partial derivatives. So here is the theorem, and it is Clairaut's theorem. And it says this: suppose our function f is defined, meaning well defined, on an open disk, right? And we know what that means. And that this is just a technical thing that needs to be on there. Again, it's something that pops up, like when you see the proof, you're like, okay, that's why that needs to be there. So an open disk containing the point, let's say x0, y0, right? So if our mixed partials f sub xy and f sub yx, so if these two things are continuous on this disk, right? So continuous at every point in this disk, not just at the x0, y0, but every point in this disk. So are continuous, and that's what Clairaut requires, continuity. So on this disk, then the conclusion is this mixed partial evaluated at x0, y0 will always be equal to this mixed partial, again, evaluated at the same point, right? So the takeaways from this is that if your mixed partial derivatives are continuous on a common disk, or let's just say domain, then they have to be equal. And if we go back to this example, look at this just as a function. This function is continuous for all x and y. This function is continuous for all x and y. That's why they are going to be equal for all x and y. And in a course like this, the functions that we study will always have this property. So Clairaut says, yeah, when you're doing your mixed partials, technically the order of differentiation doesn't matter, right? What matters is how many times you've differentiated with respect to y and how many times you've differentiated with respect to x. Not the order in which you differentiate, but just how many times you differentiate. And this, I will illustrate it even further by doing another example, but now let's do it where we have a function of three variables, right? And let's look at third partial derivatives. And I'll just do a few of them, right? Because this can get out of hand pretty quickly. I mean, we all like derivatives, but we also like our time. So here's an example. And again, I will pick a fairly simple function just to illustrate it. So let's say w is something like x squared, just e to the y, and then let's say the cosine of 4z, right? So there's our function, pretty simple. And let's go ahead and go through and compute just a few third partial derivatives. So, and I'm just going to focus on the mixed ones, right? So I am going to do, in fact, let me write down the ones that I will use or compute. So let's say we are going to do w x, y, and then x. And then let's do w, y, x, x. And then let's do w, x. Actually, let's throw a, actually, yeah, let's do then an x, x, y, right? So what I want you to take away from this is that what we're going to find three third partial derivatives, right? In that process, for each of these, we will do exactly two derivatives with respect to x and one with respect to y. And what Clairaut is saying is that as long as these functions are continuous, then our answer to all three of these will be equal. And looking at the functions here, the x squared, the e, the cosine, these functions are going to be continuous for all x, y, and z. So we would expect this condition to be met. So we would expect the conclusion to be that all of these are going to be the same, right? So let's start with this one. So if I do wx, so with respect to x, I get to treat the y and the z as constants. Now, I made it simple by making them multiples. I didn't want it to like just boil down to like a constant or to be a zero. I wanted to have, more non-zero factors in our partial derivatives, so it doesn't seem like it's just trivially true, but non-trivially true. So anyway, let's differentiate this with respect to x. So I get to treat the e to the y and the cosine of 4z as constants. Differentiating the x squared will give me 2x e to the y cosine of 4z. Now let's take this, and again I'm doing the first one, differentiate this with respect to y. So that's the e to the y term. The 2x and the cosine of 4z, these are constant multiples that will come down, right? And that was kind of the part of the reason why I made this just one big product. So if I now do wxy, I will end up getting, so the 2x will come down. The derivative of e to the y is still e to the y, and then the cosine of 4z also comes down, right? In fact, if you notice what I have here, there is no z over here, right? So we will always be treating the cosine of 4z as a constant. Now let's take this and differentiate it with respect to x again. So that means we go back to treating the e to the y and the cosine of 4z as a constant. And when I differentiate 2x with respect to x, I get this third partial derivative, 2 e to the y cosine of 4z. All right? So basically what we're going to illustrate now is if I change the order in which I do these derivatives, so if I start out by differentiating with respect to y, and then with respect to x twice, that's what this one is saying, we will end up with the same result, right? So let's do the middle one. So wy, so bring down the x squared times, because it's again multiple, the derivative of e to the y is e to the y. And again, bring down the cosine of 4z because that's another constant multiple. So we got that. Now let's do two derivatives with respect to x. So looking at this, differentiating once with respect to x gives me 2x e to the y cosine of 4z. There you go. And look, in fact, you look at this, you can see the Clairaut is also, it also applies here because this partial xy is this mixed partial is identical to this mixed partial. So then when I differentiate with respect to x, yeah, we're going to end up with the same result. So w sub y xx. So differentiating with respect to x, the 2x becomes 2, we get the e to the y, and then we bring down our cosine of 4z, right? Let me go ahead and take these off now and just say, so we're going to do wxxy. right? So W first with respect to x, so we get 2x e to the y cosine of 4z, 4z, and then again with respect to x, so wxx, so this gives me 2 e to the y cosine of 4z, and then finally now, when I differentiate with respect to y, well, it's going to be exactly the same because the derivative of e to the y is e to the y, and then the other two, this is a true constant, this is being treated as a constant for this process, so both of those come down, and we have 2 e to the y cosine of 4z, right? So again, this is just illustrating what Clairaut says. If your mixed partials are continuous, right, then the order in which you compute the partial derivatives will not affect the result. So again, just to kind of extend it, I'm not going to actually do it. I'm just going to write this down symbolically. But let's say you had your z was, or actually, let's do something like, let's say q is a function of x, y, z, and w. So let's say you had a function of 4 independent variables. Then, for instance, this. So let's say q sub x, y, x, z, z, w, 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 right? So let me write down a mixed partial that is a different order, but is guaranteed to end up giving me the exact same thing. This will be equal to, if I did w, z, x, x, y, z, w, w. I know these two must be this equal. Again, well, actually, assuming that everything is nice and continuous, right? As long as I have two x's, which I have right here, as long as I have two z's, which I have right here, as long as I have a single y, so there and there, and as long as I have three w's, there, and then there and there, as long as I differentiate with respect to each or any of my variables, right, the same number of times, not the order, so it's not the timing that's the issue. The order is as long as it's the same number of times with respect to x, with respect to y, with respect to z, with respect to w, and now I'm out of breath, but I'm going to keep going. Then I know under continuity these two would have to be equal. If I were to do like let's say one less w, so just to emphasize, this is not necessarily going to be equal. So let's say I switched one of these w's to a y. So then it's, let's say, y, and then I kept everything the same. Z, x, x, y, z, w, w. This one is not necessarily the same as these because I ended up differentiating with respect to each variable here twice, which is not what I did here, right? So it could work out, right? If for instance, if your q is a polynomial and you differentiate it enough times and you get 0, then yeah, you could end up with a situation where they're equal even though the number of times you differentiated with respect to each variable is different. But in general, we can't say that these two will always be equal. Under continuity, these two will always be equal. And there you go, higher order derivatives, and we'll see how useful these are going forward. See you then.